Okay, problem 13. Here we go. A long, straight metal rod has a radius of 5.2 centimeters and a charge per unit length of 32.2 nanocoulombs per meter. Find the electric field at the following distances from the axis of the rod, where distances are measured perpendicular to the rod's axis. All right, let's draw a picture. So first picture I'm going to do is like a frontal view of it. So this is the electric rod and it goes back this direction. And they say that the radius is 5.2 centimeters. And they want us to know what's the electric field at 5.2 centimeters. Well, there's a total charge of 32.2 times 10 to the negative 9th coulombs per meter on the rod. The thing here, though, is it's metal. Metal is pretty much by definition a conductor. Excuse me. And the electrons are free to move. So the idea is the charges, they're really electrons, so I'm going to say positive and negative charges, though really electrons are the only charges we have. We either have an excess of electrons or a lack of electrons, which gives you the positive charges. So here, we're going to say positive charges. And the positive charges want to get as far away from each other as possible. So what they're going to do is they're going to push out to the edge of the sphere. That way, they'll be able to maintain a maximum distance between themselves. What this results then is for any point on the inside, you're going to get no electric field. So from here, like this, the positives are going to push this guy this way on this side, the positives, as a positive, are going to push him this way, and the result effect is going to be 0. The difference between the previous problems, which were insulators, is they had a uniform charge density. The way you think of insulators is kind of like those Jello molds with the pieces of fruit inside. There's pieces of fruit inside, but they're not really able to flow freely inside the Jello because the Jello holds them. Conductors, I don't know a good analogy for the conductors. Electrons are just able to flow freely, not like fruit in a Jello mold. So the rule you need to know for this, and for life in general, and not life in general, just for physics, is that there is no net electric charge inside a conductor. All the electric charges situate themselves to cancel out the electric charge. No net electric charge inside a conductor. Therefore, since 2.5 is less than 5.2, this is going to be 0 and none. All right. B, though, they're asking for what is the electric field at 14 centimeters. 14 centimeters, okay. And, okay. So I'm going to redraw this picture as they use the term long. A long. So long basically means infinite. So I'm going to draw a picture. A side view. This goes on forever. It doesn't look like forever, but it goes on forever. And it has positive charges, so it's going to have charges like this. So basically what it means then with charges is that you don't get this effect where it goes sideways like this. That would mean that there's an end, and we're not worried about the end. So we have all the charges going uniformly, radially outward from the rod. That's where they're going with this. Okay, and we're looking at it a distance of 14 centimeters. So, erase these guys real quick. I'm going to say that right here is 14 centimeters, or 0.14 meters. Let's see. They say from the center, charge per unit length, All right, so it goes infinitely in both directions, so I'm going to say that we're operating at the center. Even if it's not at the center, like this is a couple, 3 more, then it'd basically be infinity on this side and infinity plus 3 on this side. But infinity, infinity plus 3, same thing, they're all infinity. So I'm going to say for the most part, we're measuring from the center. So I'm going to extend this a little bit out here. It doesn't have to be from the end. So we're going to take I can draw that better. I can draw that better. Get rid of this guy. There we go. So I'm going to take a small piece of charge here and see how that affects this area here in terms of making an electric field. So this is a little bit of Q. Do they give us a charge density? Charge per unit length, 32.2. Got it. So we have a lambda equals 32.2 times 10 to the negative 9th coulombs per meter. Okay? Which is a delta Q per delta lambda, or per delta, I'm going to say length. I'm going to say X. There we go. So this has a delta Q, it has a delta X associated with it. I'm going to call this a height H above the center. Okay? So this electric field is going to have 2 components to it. It's going to have an X component and a Y component. So this angle right here is going to be the same as that angle right there. Because if you look at it, if you draw it closer, like this, it becomes obvious. Oh, this angle is that same as that angle. It's a geometric law of something, 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 something. Okay. Do I want to use that angle? I could use a different angle if I wanted. Actually, I am going to use a different angle. Heck with that angle. That angle's for losers. So, the way I'm going to do it this way is I'm going to use this angle right here. This angle theta is the same as this angle theta. The way I did it was going to do it the other way it'd work too. I just prefer this angle. Doesn't matter, just preference in life. Right. So, right there. So, what we're going to look for then, let's see, make sure this seems kind of reasonable. If I draw something like this, then this angle will be that angle. This angle will be that angle. Yep. Theta, theta. Yes, true. Believe it. All right. So this will be the electric field generated by this little particle right here. So this then would be the cosine of theta times that electric field, and this would be E sine of theta. All we care about here is the sine of theta, because the horizontal component is going to be canceled out by the other side of the rod. So all it's going to add together then will be the sine of theta. So going back to SOHCAHTOA, we know that, oh, there we go, sine of theta equals SO opposite over hypotenuse, which equals, let's see, this guy here, opposite, which would be H, over hypotenuse, which is this guy. So H, I'm going to call this value right here X. I should probably call it negative X, but I'm not going to. It's just going to be called X. I could do it on the other side of the other side over here, and then it would just be positive X, but it doesn't matter. So this right here will be X squared plus H squared square rooted. So X squared plus H squared to the 1/2. Okay, so now we're going to write down the value or the equation for the electric field. So the electric field is going to be big K, Q, I'm going to make this a portion, there we go, over x squared plus h squared. All right, so I got to explain this. So it's over r squared, where r we already decided was x squared plus h squared to the 1/2, but we want to square it, so then we have a 2 over 2. And then we're going to multiply that by sine theta, because we're only interested in a portion of the electric field, specifically the portion that's pointing away from the line. So we're going to have then h over x squared plus h squared to the 1/2. These will then combine to become the 3/2. Okay? And then I'm going to switch out delta Q with delta Q equals lambda delta x. So we have K lambda delta x times h times x squared plus h squared, and it'll be 3/2, so now it's going to be negative 3/2. And this is going to be equal to delta E. So I'm going to take the integral, so now we have this, I'm going to change, this guy will then become dx, this guy will then become dE, I'm going to take the integral. So I'm going to rewrite this guy a little bit down. Let's go with, is that teal? I think I called the other one teal. I'm going to go with this one, call him teal. So integral of dE will just be E, and then we're going to have, I'm going to take out all the constants, K, lambda, and H. Then we're going to have x squared plus h squared to the negative 3/2, negative 3/2 dx, integral. How do I integrate that? Did I just make some sort of terrible, terrible error? I'm going to Wolfram this and see what happens. Integral of x squared plus h squared to the negative 3/2 with respect to x. Yeah, let's go with this. Oh, that worked out surprisingly well. Okay, I'm going to write that down. I am going to write that down because that looks really compact and useful. All right, there's probably I probably should figure out how to do that mathematically, but I'll do that tomorrow. I'm not going to do that tomorrow. Equals K lambda h, and it said x on top, and I think it was divided by some h squared times x squared plus h squared to the 1/2. So I guess one of these guys will cancel out, and we will be left with K lambda x over h x squared plus h squared to the 1/2. And this will be the electric field at any given radius or any given height. above it. Now, we're saying that x is infinite, so we're going to have to take the integral from, do it from 0 to infinity. What happens when we put infinity in here? We'll see. I'm just going to go from 0 to infinity and then double whatever answer I get. So we'll get k lambda x over h. So if we pull out the x squared, we'll have an x, and then we'll have an 1 plus h over x squared to the 1/2. Cancel, cancel. That blows up to an, okay. Which equals k lambda over h. So when we plug in, and then 1 plus h over x squared, so when we plug in 0, that makes this part infinite, which makes the whole thing 0. So when we have plug in 0, that becomes infinite. So the entire thing is 0 when we plug infinity. When we plug in infinity here, we get 1 plus 0, so be h, should be k lambda over h. And then we have to take into account both sides. So electric field for an infinite wire, infinite conductor at distance h from the axis will be twice this, will be k lambda over h. So we'll actually put in some numbers for this guy. But before we do, I'm going to check hyperphysics. So Google, nope, that's not what I wanted. Google, electric field of a finite line charge. Yeah, that makes sense. Electric field, line charge. All right, so this is the equation that I want. Copy, come in here, and we will paste it. Paste. Control V. There we go. Boom. Oh, nice. Is that actually the same? 2k lambda over h, 2k lambda over z. Yes. All right. So this would be worth memorizing in life, right here. But more importantly, we also have another equation over here. So if you look at this equation right here, let's lock this guy so I can draw all over him. Bam. There we go. So if we look at b over z squared plus b squared, now I'm going to look at the a side. I like the a side better. So this a is this distance right here, a, and this over here is r. So that right there, cosine of theta, so COTA is adjacent over hypotenuse. So you can rewrite this equation as k lambda over z cosine theta 1 minus cosine of theta 2, where right here is theta 1 and right here is theta 2, or in this case beta. So for example, you take this, use this equation right here and say for an infinite line charge. An infinite line charge means this thing is going to go out to infinity and this theta is going to equal 0. And over here it's going to go out to infinity and this is going to be negative 180 or negative pi. So this equals 1, this equals negative 1. both positive, it becomes 2. So for an infinite line charge, you're going to have this answer right here, 2k lambda over z. All right. So now we have our 2k lambda over z memorized. It's worth memorizing, at least for the test. We're going to find the magnitude at 14 centimeters. So E equals 2k lambda over z, which is 2 times 8.99 times 10 to the 9th. Zoom in. Times lambda. Now I need to zoom out. All right, I'm going to do the z part first, which is 14 centimeters, 0.41 meters. 32.2 nanocoulombs per meter. 32.2 nanocoulombs per meter. All right, so we got the 10 to the negative 9s cancel out. And we are left with 2 times 8.99, 2 times 8.99 times, go back over here, 32.2 divided by 0.14. Yeah. All right. So then here we're going to have 4135. Okay. 4135. And this will be newtons per coulomb? Yeah, newtons per coulomb. So this will be 4135 newtons per coulomb. And these are positively charged, so it's going to be outward from the conductor, because sources send electric field lines outward. All right, so now we're going to do the exact same thing, but with 140. So it is 10 times as far away. So it is, instead of dividing by 0.14, we're going to divide by 1.4. So I'm just going to go back here. I could probably do this in my head, but I'm not going to if I don't have to. 413.54, yes. So this is then going to be 413.5 instead of 4,000. Yep, and that seems reasonable. So a lot of talking. The derivation of this took a little while, but it's worth understanding the basics of how we did it. And what's really important then is I would just memorize this formula here, where cosine theta, theta 1, minus cosine theta 2, theta 2. That way, if on the test you're ever given a question to find the electric field due to an infinite line charge or a finite line charge, you can quickly figure it out using the formula, as opposed to going through all this and probably making a mistake just because you've been taking a test for a while already. You're probably a little bit tired, and people make mistakes in life. Memorize formula. That way, even if you do have to go through and show all your work, you'll at least know if you get the right answer. All right? Sounds good. So we got one more problem left in this section, and we're about to do it right now. All right? See you soon.